Hello friends and welcome to YouTube channel on Engineering Mathematics by Dr. Navneet. Friends, in this video lecture we are going to learn the concept finding the inverse Z transformation by partial fraction. So before starting with the actual concept, let me first introduce the concept of partial fraction. So friends, we know that if we write the given function f of z is equal to p of z upon q of z, where this p of z and q of z are the polynomial in terms of z, this is numerator and this is denominator, then partial fraction is possible only when the degree of denominator is greater than the numerator. Then we know that there are four important rules for finding the partial fraction. Here we are learning only three rules which is related to this inverse Z transformation by partial fraction. So first rule for obtaining the partial fraction is that so there may be a factor which are linear and non-repeated. So for example, if we write the given function f of z is equal to p of z, which is numerator, upon z plus a, z plus b, that means in denominator, so power of z is 1. So that's why this is called as linear, and non-repeated, this is z plus a, this is z plus b. So these are non-repeated factor. So in this case we can write partial fraction as a upon first factor plus b upon second factor, and we can continue this for remaining factor also. So now this is the first rule for obtaining the partial fraction. Now second rule is for linear and repeated factor. So here assume that f of z is equal to p of z upon z plus a, z plus b, and this z plus b factor is repeated n time. So in this case we can write the partial fraction as this is non-repeated factor, so we can write this as a upon z plus a for the first factor. Then this factor is repeated n times, so we can write this as b1 upon z plus b, then b2 upon z plus b its square. That means we are increasing power of denominator by 1. In general we can write this as bn upon z plus b raised to n. So this is for linear and repeated factor. Similarly for quadratic factor, suppose f of z is equal to p of z upon, so this is the quadratic z square plus a z plus b, and second factor is z square plus c z plus d. So this is quadratic factor because power of z is 2. So that's why this factor is quadratic factor. Now for this first factor, we can write this as a z plus b upon z square plus a z plus b, and for this second factor we can write this as c z plus d upon z square plus c z plus d. So these are the three important rules we required to learn the concept of inverse Z transformation by partial fraction. So friends, again question may get arise that so how to find the factor when the degree of numerator is greater than denominator. So we know that so partial fraction is possible only when the degree of denominator is greater than the numerator. So in some cases it may possible that so there are examples where degree of numerator and denominator may be equal, or degree of numerator may be greater than the denominator. In that case, so concept is that if the degree of numerator is greater than denominator, then in this case we are writing f of z is equal to p of z upon q of z as f of z upon z. That means we are taking some z term to the left side of this equation. So this p of z become this term may get changed, numerator may get changed. So that means we are reducing the power of denominator, degree of denominator, so that again partial fraction rule will become applicable. So this is the rule, and we are solving the example based on this rule in our next video lecture. At the time being, we are solving the example based on this inverse Z transformation with the help of partial fraction, and which is based on this three rule. Now let's take the first example. Now friends, let's take the first example. So here first example is find the inverse Z transformation of function f of z is equal to 1 upon z minus 3 z minus 2, and a region of convergence for this example is mod of z is less than 2, then mod of z lies between 2 and 3, and third region of convergence is mod of z is greater than 3. So now here, so this is the example where we are going to find the inverse Z transformation. So now here question may get arise in your mind that So when we have to apply the concept of binomial expansion, and when we have to apply the concept of partial fraction. That means we know that there are two methods for finding the inverse Z transformation. So these are the two different methods. So first method is called as binomial expansion, and second method is called as partial fraction. So second method is called as partial fraction. So here question may get arise in your mind that so when we have to apply the concept of binomial expansion and when we have to apply the concept of partial fraction. So friends, so this binomial expansion concept is applicable when we get a single term in the denominator. So when we get single term in the denominator, so power of this term may be 1, power of this term may be 2, 3, 4 and so on. Whatever power may be for this, but we get the single term in denominator. At that time, use the concept which is called as binomial expansion. But in denominator, if more than two term, that means z minus a, z minus b, that means if in denominator two or more than two term appear in denominator with power 1 or 2 or more than 1. At that time, use the concept of partial fraction. Now friends, here observe that given function is 1 upon z minus 3, z minus 2. That means in denominator we are getting two terms. So whenever two or more than two terms appear in the denominator, apply the concept of partial fraction. So why we are applying the concept of partial fraction? So after applying partial fraction concept, equation may get reduced into the standard form, so that we can apply such type of standard form for expanding the given function in terms of geometric progression or some standard form. So that is the reason why we are doing the partial fraction. So now here, this is the equation having two terms in the denominator. So we are applying first the concept which is called as partial fraction. So let's first do the partial fraction of this term. So given equation is 1 upon, this is z minus 3, then z minus 2. So we can write this as. So friends, observe that power of z is 1 and this is z minus 3, z minus 2. That means these two factors are non-repeated. So we can write it partial fraction as a upon z minus 3 plus b upon z minus 2. So now let's obtain the partial fraction. So we can write this as 1 is equal to, take this denominator to the right side. So we get this as a into, so after taking these two, this term z minus 3 term will get cancelled. So this is z minus 2 plus b, after taking these two this side, we get this as z minus 3. So now in particular, if we put the value of z is equal to 2, so that this factor become 2 minus 2 0, and we get this as 1 is equal to, so this is 2 minus 3, that means this is minus, so we can write this as minus b. So that means value of b is minus 1. So similarly, in particular, put the value of z so that this term becomes 0 and we are able to find the value of a. And it is possible when we put z is equal to 3. If we put z is equal to 3, then this become 1 is equal to a into, this is 3 minus 2, that means this is 1 into a, so we can write a, that means value of a is 1. So in this way, we get the value of partial fraction of this term where a is 1 and b is minus 1. So that we can write this term as, so 1 upon, this is z minus 3 minus 1 upon z minus 2. So this is the simple way to obtain the partial fraction of given example. Now friends, after obtaining the partial fraction, so now let's try to solve the example with the help of given region of convergence. So here, so first region of convergence is mod of z is less than 2. So now we know that how to solve the example based on inverse Z transformation. So before solving example based on inverse Z transformation, so please try to understand that how we are solving example based on Z transformation. So whenever we solve example based on Z transformation, so first write down the definition of Z transformation. So then here k goes from minus infinity to plus infinity, uk z raised to minus k. Then in particular put the value of k in such a way that we get such type of expansion. So after after expanding this summation sign, so there are two possibilities. First possibility is that we may get the value of geometric progression, or it may possible that we get the expansion of some standard function. So after getting expansion of standard function of geometric progression, we are writing its sum and we are writing the region of convergence as mod of r less than 1. Now for finding inverse Z transformation, exactly do the reverse steps. That means from region of convergence, so find the sum, and based on the sum try to find out such type of expansion, and based on this expansion find out the coefficient of z raised to minus k, and coefficient of z raised to minus k is uk, sequence uk, and we know that according to the definition of inverse Z transformation of uk is equal to f of z, then we can write its inverse Z transformation as uk. That means coefficient of z raised to minus k is uk, and which is inverse Z transformation. So while solving such type of example, so first find out the region of convergence. So now here mod of z is less than 2, so this indicates that z upon 2 is less than 1. So z upon 2 is less than 1. So now try to write the given function in terms of 1 upon 1 minus r. So here let's write the given function as f of z is equal to, so given function is this function, and after partial fraction we are getting this type of term, so we can write this as 1 upon minus this is 1 upon. So now friends, here please try to understand that, so for a given condition mod of z is less than 2, so value of r is z upon 2. So that means from this second factor take the term z upon 2 common, so we get this as z upon 2 minus 1. That means we have to take the term 2 common. So after taking 2 common from this denominator, we get this as z upon 2 minus 1. Now here please try to understand that, so here z upon 2 is the region of convergence, and based on this region of convergence it is possible for us to take the term 2 common. But what about this term? So here we cannot write region of convergence as z upon 2 here, so it is not possible to write z upon 2 common. Now but friends, try to understand that mod of z is less than 2, so it's obviously says that as mod of z is less than 2, so this implies that mod of z is also less than 3, because z is less than 2, it indicates that mod of z is less than 3, because here term is 3, that's why we are taking this as 3. So therefore we can write this as mod of z upon 3 is less than 1. So in this way we find the region of convergence for this first factor. So this is the region of convergence for the second factor. In this way we get the region of convergence for the first factor. Now here value of r is z by 3. So try to write this as z by 3. So we get this as z upon 3 minus 1, and it is possible when we take the term 3 common. So this is just an adjustment. So this is the case we are getting by assumption. That means obviously. Now after getting this term, our next aim is try to convert this denominator in terms of this standard form, so that we can apply the concept of binomial expansion. So for binomial expansion we require first term as 1. Now here we get first term as z by 3 for the first factor, and for this second we get this term as z by 2. Now to get 1 as the first term, let's reverse the position of first and second term. So we can write this as 1 upon, this is minus 3. So 1 upon minus 3, then we get this as 1 minus z upon 3. Again this is minus 1 upon minus 2, then this is 1 minus z upon 2. So friends, in this way we get this equation. So we resemble this term first and second, because for using this standard formula we require 1 as the first term. So moreover we can write this as minus 1 upon 3, 1 minus z upon 3 raised to minus 1, then this is minus and this is minus become plus, this is 1 upon 2, then 1 minus z upon 2, so this raised to minus 1. After taking in the numerator we get power of this term as minus 1. Now friends, our next target is to expand this first factor and this second factor. So we can write this as minus 1 upon 3 which is outside the bracket. Now if we observe this term, then this is 1 minus z upon 3 raised to minus 1. That means this is of the type 1 minus x raised to minus 1, and its expansion according to the binomial expansion is 1 plus x square plus x cube plus x raised to 4 and so on. With the help of this binomial expansion formula, we can expand this first bracket as 1 plus x, that means this is z upon 3 plus x square, that means this is z upon 3 its square plus z upon 3 raised to 3 and so on. In general, we can write its kth term because we are interested in the coefficient of z raised to minus k. That's why in particular we write the k term as z upon 3 raised to k plus and so on. So in this way we get the expansion for the first bracket. Now friends, let's try to obtain the expansion for the second bracket, this 1 upon 2 as it is. Now here observe that again term is 1 minus z by 2. That means this is of the type 1 minus x raised to minus 1. So such type of binomial expansion is applicable. So according to this we can write this as 1 plus x square and so on, where the value of x is z by 2. So we can write this as 1 plus z upon 2 plus z upon 2 its square plus z upon 2 its cube and so on. In general we write this as z upon 2 raised to k and so on. So here we get the expansion of this first bracket and second bracket according to this binomial expansion. Now friends, this 1 upon 3 is constant. Now take this to inner side. So we get this as minus. So in bracket this is 1 upon 3 plus z upon this 3 and this 3, we get this as 3 square plus this is z square, then z 3 square and 3, we get this as 3 cube plus this is z cube upon this is 3 raised to 3 cube and this 3, that means 3 raised to 4 and so on. In general we write this as z raised to k upon 3 raised to k plus 1, because power for this term is 3 raised to k and this 1 3 is there, that's why this power of 3 is 3 raised to k plus 1 and so on. So again if we try to take the term 1 upon 2 to inner side, then we get this as 1 plus this is z upon 2 into 2, we get this as 2 square plus next is z square upon this is 2 square into 2, we get this as 2 cube plus this is z raised to 3 upon this power is z cube and this z 2, that means we get this as 2 raised to 4 and so on. But our main interest is to get the value of z raised to minus k. Now if we take this 1 upon 2 to the inner side for the k term, then we get this as z raised to k upon 2 raised to k plus 1 and so on. In this way we can obtain the expansion of this term. That means from region of convergence we obtain the sum, and according to the sum we get such type of geometric progression or standard expansion of function. Now our next target is to obtain the value of coefficient of z raised to minus k, which is uk, and uk indicate the value of inverse Z transformation sequence. Now friends, if we try to obtain the coefficient of z raised to k, so now here the power of z raised to k is positive, so we can take k, we can replace k by minus k. So therefore coefficient of z raised to k equal to, so this minus sign is there, so we can write this as minus 1 upon 3 raised to k plus 1. So now here again question is that we can write this as minus 3 raised to this is minus k minus 1. So in this way we can easily write this in the numerator. Again here friends, question is that find the condition on k, because whenever we write the definition, in definition we are writing the value of k from minus infinity to infinity. So to find the value of k for this bracket, so in particular in this kth term, put the value of k in such a way that we get this as the first term, this as the second term, this as the third term, this as the fourth term and so on. Sorry. Now friends, here after taking k is equal to 0, we get this as the first term. Because k is equal to 0, we get this as 3 raised to 1, and z raised to 0 means 1, we get this as 1. That means it is possible when k is equal to 0. Now if we put the value of k is equal to 2, then 3 raised to 1, k is equal to 1, then this is 1 plus 1, 2, we get power as 1, z raised to 1. So that means k is equal to 1. Next value is k is equal to 3, 2, 3 and so on up to infinity. That means in simple way we can write this as k is, this indicates that k is greater than or equal to 0. But friends, here we get the coefficient for z raised to k. But our interest is to get the value of coefficient of z raised to minus k. So therefore we can write this as, therefore coefficient of z raised to minus k is equal to, that means replace k by minus k. So we get this as minus 3 raised to k minus 1, and when we replace k by minus k, then this inequality will get changed. So this become k is less than or equal to 0. So here this is the coefficient of z raised to k for the first bracket. Now similarly obtain the coefficient of z raised to k for the second bracket. So this is for first term. So this is for first term. Now similarly obtain the coefficient of z raised to minus k for the second term. So let's obtain for second term. So for second term, let's obtain second term. So therefore here coefficient of z raised to. So again here power of k is positive, so we can write this as z raised to k, and this coefficient is here plus sign, and this is 1 upon 2 raised to k plus 1. So we can write this as 2 raised to minus k minus 1. Again friends, try to obtain the condition on k. So in particular put the value of k in such a way that we get first term as 1. Put the value of k is equal to in such a way that we get second term as z upon 2 square and so on. So friends, here so this is possible only when we put the value of k is equal to 0. So then we get this as, so sorry, by default here, so if we multiply this to the inner side, then this is 1 upon 2 into 1, so we get this as 1 upon 2. So this is mistake. Now friends, in particular put the value of k in such a way that we get first term as 1 upon 2, second term as z upon 2 square and so on. So then this is possible when we put k is equal to 0. That means here we put k is equal to 0. Then put k is equal to 1, we get this term. So k is equal to 2, we get this term and so on. This goes to infinity. So in short, we can write the value of k as greater than or equal to 0. So here we get the value of z raised to k coefficient. So therefore we can write the coefficient for, therefore we can write the coefficient of z raised to minus k is equal to 2 raised to, this is k minus 1. We are replacing k by minus 1 where so after putting k by minus k, so this inequality will get changed. So k is less than or equal to 0. So now friends, here please try to understand that. So we obtain the coefficient of z raised to minus k for this first term, and this is the coefficient of z raised to minus k for the second term. So to find out the inverse Z transformation, we will combine this term. This is the first term and this is the second term. So we can write this as therefore inverse Z transformation of sequence given function f of z is equal to sequence uk. So according to the definition of inverse Z transformation, uk is equal to inverse Z transformation of f of z. So it's inverse Z transformation. Its inverse Z transformation means inverse Z transformation of this term. So we can write its inverse Z transformation as so here we get first answer as, so this is the answer which is related to the first term, and this is the answer which is related to the second term. So whenever we write the answer of such type of inverse Z transformation, try to understand the condition on K. So here K is less than 0, here also K is less than 0. So we can combine these two terms because condition on K is same. So now here for this first term, value of this term is minus 3 raised to K minus 1, and here middle sign is minus, so we can write this as minus. So this minus is because of this middle sign. Sorry, this is minus, so here we get this coefficient as plus, so after this minus we get this as plus, so this minus become plus here, so this minus 1 has become plus, so we can write this as plus, then 2 raised to K minus 1, where K is less than or equal to 0. So in this way we can easily solve the example based on the inverse Z transformation. So this is the solution of this first problem for the first region of convergence. Similarly, we are solving for second and third region of convergence. Let's take the solution for the second region of convergence. Friends, let's take the solution for the second of region of convergence. So a second region of convergence is that mod of Z is lies between 2 and 3. So we can write this as 2 is less than mod of Z, so that we can write this as 2 upon Z is less than 1. And a second condition is that, so here mod of Z is less than 3, we can write this as Z upon 3 is less than 1. So this is because of the region of convergence, mod of R is less than 1. So that's why we get the value of this term as less than 1 and this term as less than 1. So now try to write the given function as, so given function is f of Z is equal to, so here 1 upon Z minus 3 and this is Z minus 2. So for this 1 upon Z minus 3, value of this R is Z upon 3. So we can write this as, so Z upon 3, that means we can write this as Z upon 3. So after taking 3 common, we get this as Z upon 3. So for region of convergence, mod of R is less than 1. To obtain such type of term, so we are taking 3 as common. So now this is for the first, now middle sign is minus, this is 1 upon. Again, write down the denominator of this term in such a way that we get this as 2 upon Z. Then 2 upon Z, that means this is 2 upon Z is possible only when we take the term Z as common. So after taking Z common, we get this as 2 upon Z. Now friends, please try to understand that. So this second term is in our standard form, 1 plus x form. But this first term is not in the standard form. So reshuffle first and second term. So we get this as 1 upon, this is minus 3. So after taking minus 3, we get this as 1 minus Z upon 3. So this is minus 1 upon Z. In bracket, we get this as 1 minus 2 upon Z as it is. So there is no need to reshuffle this second term because this is in standard form. This was not in the standard form. That's why we convert this into the standard form. So if we try to readjust this term, then we get this as minus 1 upon 3 as it is. Then this is 1 minus Z upon 3 raised to minus 1. Then this is minus 1 upon Z, 1 minus 2 upon Z raised to minus 1. So in this way, we get the term in the numerator. So when we take term in the numerator, power of this term become minus 1. So now our aim is that, so this is the region of convergence, this is the region of convergence. Our aim is to write the given equation in terms of 1 upon 1 minus r. Now this is 1 upon 1 minus r form. Now our next aim is to get such type of expansion of function. Then such type of expansion of function is possible when we expand this first and second bracket. So if we try to simplify this, then we get this as 1 upon 3 then in bracket. So friends, please try to understand that here. So this term is 1 minus z by 3. That means this is of the type 1 minus x raised to minus 1. Its expansion is 1 plus x square plus x cube and so on. So if we try to apply this concept here, then we get this as 1 plus value of x for this first term is z by 3. So we get this as 1 plus z by 3 plus z by 3 its square, and so on. But our main interest is to get the value of coefficient of z raised to minus k. That's why we write the z raised to k coefficient. So this is z upon 3 raised to k, and so on. So in this way we get the expansion for the first term. Then similarly we can write this as 1 upon z. Then again try to expand this second term. Again second term is of the form 1 minus x, where value of x is 2 by z. So according to this formula we can write its expansion as 1 plus, this is 2 upon z plus 2 upon z its square plus, and so on. But our main interest is to get the value of coefficient of z raised to minus k. That's why we can write the kth term, so 2 upon z raised to k, and so on. So in this way we get the expansion for the first and second term according to this binomial expansion form. So now friends, take this 1 upon 3 to the inner side and this 1 upon z to the inner side. So we get this as minus as it is. Then this is 1 upon 3 plus this is z upon 3 square plus this is z square upon 3 cube, and so on. In general we get this as z raised to k upon 3 raised to, this power is 3 raised to k and this is 3, so we get this as 3 raised to k plus 1, and so on. So this is our interest, z raised to k is our interest. So we may replace this k by minus k so that we get this term. So now let's try to take 1 upon z to the inner side. We get this as 1 upon z plus 2 upon z square, after taking this z into z square, plus this is 2 square upon this is z square into z, we get this as z cube, and so on. So we get this as 2 raised to k, so this is 2 raised to k upon z raised to k, and this z we get this as z raised to k plus 1, and so on. But friends, here please try to understand that we get the value of z raised to k here directly, because to find out the inverse z transformation means what? Find out the coefficient of z raised to minus k. So here we get the coefficient of z raised to k, we may replace k by minus k, so we can easily get here. But here we get the value of this coefficient as z raised to k plus 1, but we are interested in only value of z raised to minus k. So that's why write down one previous term. So one previous term is 2 raised to k minus 1 upon this is z raised to k. So now here we get the value of z raised to minus k. So our purpose will get solved after writing this term. So now friends, for this first term, that means for this first term, coefficient of z raised to k equal to, so this minus sign as it is, and its coefficient is 1 upon 3 raised to k plus 1. We can write this as minus, this is 3 raised to minus k minus 1. Again here put the value of k in such a way that we get this as the first term, this as the second term, this as the third term, and so on. This is possible when k is equal to, so here the value of k is equal to 0, then this is k is equal to 1, k is equal to 2, and so on. That means this value of k starts from 0 to infinity. That's why we can write this as k is greater than or equal to 0. So this is for the first term, but our aim is to get the value of coefficient of z raised to minus k. Here we get coefficient as z raised to k. So therefore coefficient of z raised to minus k is equal to minus 3 raised to k minus 1, k is here less than or equal to 0. So in this way we get the coefficient of z raised to k minus k for the first term. Similarly for second term, so for this second term, coefficient of z raised to minus k is equal to, here we get directly value of z raised to minus k, because z raised to k is present in the denominator. So after taking in the numerator we get this as z raised to minus k, and its coefficient is this minus sign as it is, then 2 raised to k minus 1. Now again here a question is that find the condition on k. In particular, put the value of k in such a way that we get this as the first term, this as the second term, this as the third term, and so on. So then this is possible when we put k is equal to 1. If we put k is equal to 1, then z raised to 1 is z raised to 1. Then this is 2 raised to 1 minus 1 is 0, that's why 1. Then this second term, k is equal to 2, k is equal to 3, and so on. That means here k goes from 1 to infinity. So that's why we write the condition as k is greater than or equal to 1. So now friends, our aim is to find out the inverse Z transformation. So therefore inverse Z transformation of f of z. So we can write this inverse Z transformation as sequence uk, and which is given as. So now friends, here a given function is 1 upon z minus 3, z minus 2. We can obtain its partial fraction. This is the answer to the first term, and this is the answer to the second term. So while writing the final answer, so concentrate on condition on k. So here k is less than 0 and this k is greater than 0. So we cannot combine these two answers together. So we can write this condition as minus 3 raised to k minus 1, and this is possible when k is less than 0, and value of sequence uk is equal to, this is minus 2 raised to k minus 1, and when k is greater than or equal to 1. So in this way we can split this into the two parts, because condition on k for first and second term is different. That's why we split this into the two parts. Now friends, this is the second example, this is the example with region of convergence as mod of z lies between 2 and 3. Now let's take the solution for the same example when mod of z is greater than 3. Now friends, third region of convergence. So region of convergence is mod of z is greater than 3. So this third region of convergence is mod of z greater than 3. So we can write this as greater than 3. So moreover, we can write this as mod of z upon 3 is greater than 1. But according to our requirement, we require the value of mod of r less than 1. So here we get greater than 1. So after taking reciprocal, we get this as 3 upon z is less than 1. So here we get the region of convergence. So if we try to write the given function f of z is equal to, so here we get the value of r as 3 upon z. Then this 3 is present for the first term, so we can write this first term as 1 upon. So this is 3 upon z, and then according to the sum of geometric progression formula, we can write this as 1 upon 1 minus r form. So this is possible when the value of r is 3 by z. So then to get 3 by z, so we get this as 3 by z term, and this is possible to get 3 upon z term from this z minus 3 when we take the term z common. So if we take z common, then this is 1 minus 3 by z. So this is the first term. But question is that what about this second term? So for this first term only, condition is given that mod of z is greater than 2. So their condition for this second term is not given. So but here please try to understand that mod of z is greater than 3. So as mod of z greater than 3, so this directly indicate that mod of z is also greater than 2. Obvious, this is obvious thing, because this is 2, that's why we take this as 2. So mod of z is greater than 3, this indicates that mod of z is also greater than 2. So we can write this as z upon so we can write this as z upon 2 is greater than 1. Moreover, we can write this as 2 upon z is less than 1 according to this region of convergence. Now friends, if we try to write this second term as, so here a minus sign. So now we require here value of r as 2 by z. So we can write this as 1 upon 2 upon z, and this is possible when we take the term z common again from the second term. But after taking z common, we get this term. After taking z common, we get same term. This equation as well as this equation is in our standard form, because for the standard form we require 1 as the first term. So we can write this as 1 upon z, then 1 minus, this is 3 upon z. So after taking this in the numerator, we get this power as minus 1 minus this is 1 upon z, then this is 1 minus this is 2 upon z raised to minus 1. So after taking the numerator, we get such type of term. Now friends, our next aim is that, so that means we get this equation in this geometric progression sum form. Now next aim is to get such type of expansion so that we obtain the coefficient of z raised to minus k. Now try to expand this term, so we get this as 1 upon z as it is. So here this term is of the type 1 minus x raised to minus 1. 1 minus x raised to minus 1. Its expansion is 1 plus x square and so on. So where the value of x is 3 by z. So we can write this as 1 plus 3 by z plus this is 3 by z its square and so on. Our main interest is in the k term. So we can write this as 3 upon z raised to k and so on. So here friends, we get the expansion for the first term. Now second term is 1 upon z. Again apply the same formula, 1 minus x raised to minus 1, where the value of x is 2 by z. So we can write this as 1 plus 2 by z plus 2 upon z its square and so on. Our main interest is k term. So we can write this as 2 upon z raised to k and so on. So we get the expansion for the first and second term. If we take this 1 upon z to the inner side, then we get this as 1 upon z plus this is 3 upon z square plus this is 3 square upon z cube and so on. So here we get the power as z raised to k and this is z. So we get the power of z as z raised to k plus 1. But our interest is k power only. So that's why we can write this as z raised to 3 raised to k minus 1, previous one term, upon z raised to k minus 1 into z, we get this as z raised to k plus this is z raised to k 3 raised to k upon z raised to k plus 1 and so on. So here this is the expansion for the first term after taking 1 upon z to the inner side. So here we take this as the previous step because we are interested in the power of z raised to k. So if we take multiplication of these two terms, then we get this as 3 raised to k upon z raised to k plus 1. Now let's try to simplify the second term. Again take this 1 upon z to the inner side, we get this as 1 upon z plus 2 upon z square plus 2 square upon this is z cube and so on. So again after taking this z to the inner side, we get this as 2 raised to k upon z raised to this is k plus 1, because this is z raised to k and this z we get this as z raised to k plus 1. But our interest is to only get the value of z raised to k. So that's why let's write down the one term previous. So this is 2 raised to k minus 1 upon z raised to k and so on. So in this way we obtain the expansion for the first and second term. Now friends, here for first series, so this is the first series and this is for the second series. For second series, our aim is to obtain the coefficient of z raised to minus k. Sorry. Now here coefficient of z raised to minus k equal to, so this term is present in the denominator. After taking the numerator, we get this as z raised to minus k and its coefficient is 3 raised to k minus 1. Now friends, in particular put the value of k in such a way that we get this as the first term, this as the second term, this as the third term and so on. So then this is possible when we put k is equal to 1. So that means condition on k is that k is 1. Then this is possible when k is equal to 2, k is equal to 3 and so on. So that means we can write this as k is greater than or equal to 1. Or some people may write this as k is strictly greater than 0. So both ways, k is greater than 1 or k is strictly greater than 0, we can represent the value of k. Now for this second series, coefficient of z raised to minus k is equal to, So this is z raised to k, its coefficient is, this is minus sign, then this is 2 raised to k minus 1. Again find the condition on k. So in particular, put the value of k in such a way that we get this as the first term, this as the second term, third term, and so on. So this is possible when k is equal to 1, this is for k is equal to 2, k is equal to 3, and so on up to infinity. That means this is k is greater than or equal to 1. Or simply we can write this as k is greater than 0. So both way it is possible. So now friends, here this is the value of z raised to minus k for the first series, and this is the value of z raised to minus k for the second series. Now to write the final answer, we can write this as inverse Z transformation of f of z is equal to sequence uk, and we know that coefficient of z raised to minus k is the value of sequence uk, and this is the first value and this is the value of second. So now while writing the answer, check the condition on k. So this condition on k and this condition on k is same, so we can write the answer as 3 raised to k minus 1 minus 2 raised to k minus 1, where k is greater than or equal to 1, or some people may write this as k is strictly greater than 0. Now friends, this is the answer to the question. Again, if we try to write the answer in terms of minus infinity to plus infinity, then we can write this as 0 for k is less than or equal to 0. So this is the way to write the answer. So we may write this step, or we may write up to this step. So friends, here we solve only one example with the help of 3 region of convergence, first, second, and third. So I hope you people like this lecture. So thanks one and all for watching this video. Thank you.